I like talking about
Is it on? Okay. It's amazing how I always wonder how come people are, can't tell if the mic is on or not when they're giving a talk, but you really,
Can you?
yeah.
I can hear the difference here.
Barely.
I think you mostly hear your own voice like through your jaw or something like that. You don't hear it like from
Wow. I'm gonna get one of these for my house, so every time.
So you can see this where?
On the website.
The website.
How legible was my writing?
Really good. I actually checked that out.
Okay, good. I was wondering something.
That's really good. That's really good.
And then all this laser is just making everything white.
There's nothing we can do about that.
Otherwise, you just want to use document that.
Well,
No, well, it's better to be writing.
I can't actually drink my tea. We're going to have to leave on 5 minutes. Bring it back. Nothing like, oh, it does. Yeah, things like, there is no choice but to violate the rules. Week, so we're going to
Cool.
You can also hear voice in the document camera in the web.
Yeah, I think so. That's the microphone.
Is it recorded or is it just streamed?
I can go back and watch myself talk.
Yeah, you should do that because some student from Western, for instance, cannot come because in London, Ontario, so this was requested.
Do you know how many people were intending to watch this that couldn't get it?
I have no idea.
My chair already has saved them.
This watch and then
The computer
this is different.
It's so amazing how that works. Like, how it's functioning, like something runs a lot, all of a sudden it's like something like I think it's scary.
Is everybody here?
No, when I go out, that's all.
It's really strange live right now, but it will be posted on the website after 2 weeks.
2 weeks? A little bit of places on the actually, I know quite a lot, also quite a lot. You probably do it in the service case. No, I also do that.
Okay, so second talk is arithmetic techniques in mirror symmetry by Perunicic.
Thank you.
Thank you for coming.
So let me first try to motivate what I will be talking about. By pointing out what I mean by arithmetic techniques in mirror symmetry, and in particular where they came from. So in about 2000, Candelas, De La Osa, and Rodriguez Villegas studied Calabi-Yau manifolds over finite fields. or initiated the study of Calabi-Yau's over finite fields. And in particular, they started by examining the arithmetic of the quintic threefold. Which is a hypersurface given as the vanishing set of the following polynomial in 5 variables, x4, x5, x1 through x5, given as the sum, as I goes from 1 to 5, of xi to the 5th, minus some parameterized term, the psi being a parameter. And the term is just the product of all the variables from 1 to 5. And now usually you can see the vanishing set of this polynomial as living in C5, or rather P4, in which case the psi here is a holomorphic parameter. But in the case that psi is in the finite field, say that it's in the finite field with P elements, then you can consider the hypersurface P psi equals to 0. And let's say it's a subset of Fp to the 5th. This is some set of points. And then you can ask the question, what is the number of points inside on this hypersurface? And typically, since this, so over the complex numbers, since this family depends holomorphically on psi, it turns out that you can perform differentiation with respect to psi. And there's an ordinary differential equation called the Picard-Fuchs equation. So in this differentiation, so with respect to d over d psi, which has as a principal solution, one of the solutions, let's call it f of psi, the following series. So 5m factorial divided by m factorial as m goes from 0 to infinity, with 5 psi to the minus 5m as your variable. Yes, thank you. Okay, so this is a solution to ordinary. Oh, sorry, the differential equation with respect to d over d psi that we obtained from the quintic threefold, and in particular, it's the differential equation satisfied by the periods. So the Picard-Fuchs equation solved by the periods, the holomorphic periods of the quintic threefold, and they're just the integrals over some 3 cycle, because it's a 3-dimensional manifold, over a holomorphic 3 form, top form. So this here is a holomorphic 3 form. And this is some cycle. In other words, this expression here is an expression for one of the periods, and you can get the other ones, in this case, if you just find the other solutions to this differential equation. But in any case, just keep in mind that there is some differential equation associated to this hypersurface, and that the solutions are well known and given as a power series of that form. So the actual content of the paper from 2000 that I mentioned is that if you now take, instead of psi, a complex parameter, but as a number in Fp, so now we're back to the arithmetic setting where this is just a hypersurface with sets of, is a collection of points in Fp to the 5th. And you assume that 5 doesn't divide p minus 1, where p is your prime. Then the number of points on this hypersurface, which I will denote nu psi in with coordinates in Fp. So this is the Fp rational point, is given by sum from m equals 0 to p over 5, rounded down, 5m factorial over m factorial to the 5th times 5 psi to the minus 5m. And let's assume that psi is not 0, modulo p. So I can express the number of points in this hypersurface in terms of the periods of the hypersurface, interpreted in the appropriate way. And furthermore, if you retain this condition that 5 doesn't divide p minus 1 more generally, so this is just a result modulo p, but more generally you can say that the number of points with coordinates in fp on the nose equals 1 plus p to the 4th plus the sum from m equals 1 to p minus 2 of g m to the 5th divided by g to the 5m, and I'll tell you what these are in a second, times tike to the m, 5 psi to the minus 5th, where now gm is the mth Gauss sum associated to two characters from fp to p-adic numbers, and tike is a multiplicative character from fp, let's say star, to zp. So here again, these two expressions are kind of similar. And that's not a coincidence, because the way you compute the number of points with coordinates in fp on this hypersurface, modulo p and in general, is very similar. And so today I will actually talk about how to do these two computations, which I think is the result is kind of remarkable, because why should the series that describes the periods of a hypersurface have anything to do with the number of points of that hypersurface when considered over a finite field? Okay, so that was kind of the motivation for why you should care about everything that comes next. Oh yeah, sorry, I forgot that I had more boards, but you don't really need that anyway. All right. So part 2 here is character formulas modulo of p. So let's start with the lemma. So take n to be some natural number. Then the sum over all x in fp star of x to the n equals 0 mod p if n is not congruent to 0, mod p minus 2, and minus 1 mod p if n is congruent to 0, mod, p minus 1. Okay. It's actually very easy to prove. So I'm going to go ahead and do it. No. Oh, yes. This one should be is congruent to 0. Okay. So let me tell you why this is true. Just a little simple expression. So first of all, fp star is cyclic, and it has a generator, call it y. It's of order p minus 1. Okay? So now consider just the equation for the n given in the lemma, y to the n times the sum of all x in fp star x to the n. Well, we can just rewrite this as the sum of xy to the n of all x inside of fp star. And there's no need to write xy to the n because as x goes to fp star, then x times y, for y some member of fp star also goes to fp star. So this is sum of x in fp star x to the n. Okay, and so what does that mean? That means that y to the n minus 1 times the sum of x in fp star x to the n equals 0. And so what happens? In the case that n doesn't equal some k times p minus 1, then since y is a generator of fp star, it's of order p minus 1, and since n isn't a multiple of p minus 1, this isn't 1, so this first term isn't 0, which means that the second term has to be 0 in fp. So the sum of x to the n x in fp star has to be 0 in fp. And if it's 0 in np, that means if you lift it to the integers, then this is congruent to 0 mod p. And now if n is a multiple of p minus 1, well, then it's easy because any number in fp star, when you raise to p minus 1, is just 1. So you're adding 1 p minus 1 times. And this sum is just p minus 1, or modulo p is just minus 1. Proves the lemma. Okay. And so it turns out that this lemma is more or less everything you need to count points on that quintic threefold. So I think this is next. Excuse me. Okay. So let's consider an example. And instead of considering the quintic threefold, I'm going to take the Fermat cubic. Which is an elliptic curve given by the following, the vanishing set of the equation p psi x1 and x2, x3. So it's in 3 variables. And it's given by x1 cubed plus x2 cubed plus x3 cubed minus 3 psi x1, x2, x3. So this is essentially the 3-variable version of the quintic threefold equation. And so now I want to compute the number of points. The size of this set. In particular, I will compute the number of points with coordinates in fp star. The difference is very small, but this is going to be computationally a little more convenient. So can everyone see this part of the board? Okay. So what does this equal? So this equals the sum over all x in f p star cubed times of over 1 minus p psi of x, where now x is x is a multivariable. It's x equals x1, x2, x3, to the p minus 1 mod p. And here x equals x1, x2, x3. Okay. And now why is this true? Well, if if x1, x2, x3 equals x plugged into p psi is a solution, then p psi equals 0 at that point. So the summand, the corresponding summand for that chosen x just becomes 1 minus 0, which is 1. Okay? And so we're adding 1 to the count of points with coordinates in fp star. But if f psi of x is not 0, then I'm raising that non-zero number in fp to the p in fp star to the p minus first power. So that number has to equal 1, and you get 1 minus 1, 0. So that any non-zero, so when x isn't a solution, that number is not counted in this sum. So it's just a simple-minded counting of points. Now let's actually work with this expression. So I'm going to call a new psi star just the number of points with coordinates in fp star, meaning that expression. So first, I get the binomial theorem applied to this part of the sum. The p cubed here comes from, sorry, p minus 1 cubed comes from just adding all these ones. So get p minus 1 cubed. And then the binomial theorem applied to the p psi to the p minus 1 just says that you get a sum from m equals 0 to p minus 1 of p minus 1 choose m, x1 cubed plus x2 cubed plus x3 cubed to the m times minus 3 psi x1, x2, x3 to the p minus 1 minus m. And this is all modulo p. So I'm gonna omit saying modulo p just to save some time and space. And so what does this equal? Well, this equals p minus 1 cubed. Again, you can reduce this modulo p if you would like, minus the sum from m equals 0 to p minus 1. And now you have p, I'm just going to copy p minus 1 choose m minus 3 psi to the p minus 1 minus m. And now I'm going to use the multinomial theorem to expand this term. Okay? And you get a triple sum. Or sorry, you get a sum over m1, m2, and m3 such that m1, m2, m3 add up to m times this multinomial coefficient, m1, m choose m1, m2, m3. Right. Let me write it here. So this is the product. So you get 3 identical terms of okay. So xi to the p minus 1 plus 3mi minus m. That. Okay. So I just apply the multinomial theorem to this, where so it's like x1 to the 3m1, x2 to the 3m2, x3 to the 3m3, where m1, m2, m3 add up to m, and m goes between 0 and p minus 1, so you can write it this way. And now, at this point, we have what? We have a double sum, so it's a sum over m and then over all these m1, m2, and m3s. And then you have a product of sums of this form. But sums of this forms are sum over elements in fp star of x to some power. So by the character formula above, what I need is that this term here is actually a multiple of p minus 1. Because if the exponent here isn't a multiple of p minus 1, then you end up being 0 modulo p. And when you're counting points modulo p, those terms don't contribute anything to the sum. So I'm now trying to solve the equation p minus 1 plus 3mi minus m congruent to 0 modulo p minus 1. Okay? And those are going to be the surviving terms, and those are going to give me some kind of expression for the number of points. Okay. So, as I said, 3mi minus m has to equal some ki p minus 1. For now k I greater than or equal to 0, and I equals 1, 2, and 3. This is a condition for these terms to not vanish, and therefore that corresponding sum not to vanish. And in fact, I'm going to make a small claim that I will let you prove yourself, unless you really want to see it now, in which case you should just say so. For any given m, so m is the outer sum here, m ranges from m goes to 0 to p minus 1, we have m1 equals m2 equals m3. And this is, it's very easy to prove. You simply, you play a little bit with these expressions, and you use the fact that ki is greater than or equal to 0, and that, that the three of them add to m, and that m goes, that m is never greater than p minus 1, and you get that result. But if all the mi are the same, I can just let I'm sorry. Yeah, if all the mi's are the same, then 3m1 equals 3m2 equals 3m3 equals to m. Okay. And because m1 plus m2 plus m3 equals to m. And then plugging that back into this expression just gives you that the number of points with coordinates in fp star is given as the sum k equals to 0 to p minus 1 over 3 rounded down. So now I'm taking all possible values for every mi. The coefficient is p minus 1 over 3k because m equals 3k times 3k, choose kkk, times minus 3 psi to the p minus 1 minus 3k times minus 1 cubed mod p. And that equals the sum, as k goes from 0 to p minus 1 over 3 rounded down, 3k factorial over k factorial cubed, 3 psi to the minus 3k. Okay, modulo p. So here, I just got rid of this negative sign because it appears both here and here. And I simplified this coefficient modulo p to that. You, I guess, have to trust me that that simplification is correct. By the way, the multinomial coefficient is just 3k factorial divided by k factorial cubed. Yeah. And this, if you had done it for the quintic threefold, you would have just ended with 5s instead of 3s, and maybe the sum would have extended over more terms, and you would have ended up with the formula I said at the beginning. Yes?
I took m to be p minus 1 and m1 to be p minus 1 and m2 and m3 to be 0. Is that going to cancel out that p minus 1 cubed term?
If you took one of, so I see. M is p minus 1, and the other guys are 0. Yes. Thank
using a 3.
Yeah, because it suddenly disappeared. Yes, thank you. Should have said that. Okay. So this was just some simple. You had this character formula. You add points over FP. You get 0 or -1 depending on what the exponent is of x to the n. And the idea is you want to now use the same sort of methods to count points without the modulo p restriction. Well, maybe you can take this equation, and maybe you can consider some better alternative that is good modulo p squared. In fact, if you raise p psi to the p minus 1 times p, you're going to accomplish that. But that still doesn't give you a number of points because modulo p squared isn't good enough. You need modulo p cubed. And if you consider more variables, you need modulo p to whatever the number of variables is, because that's the most points you can have. So this isn't really the right way to go about it. And the right way to go about it is to generalize this computation by using p-adic numbers. So let me talk about p-adic numbers. Just a small amount of time. Okay. So p-adic chapter formulas. So since I'm probably talking to a room of physicists, I'm going to assume it's been a while since you've been dealing with p-adic numbers in any non-trivial way. So as I said, to count points without modulo p restriction, we will need p-adic numbers. And so, given some n, m times p to the nu, where now n is just an integer, m is a number relatively prime to p, so you extract the highest power of p you can from this integer. Then you can define its absolute value, p-adic absolute value, to just be 1 over p divided by to the nth power. So here, or let's use v instead. Sorry. Okay. So for example, if you have 5 squared, so 25, n equals 25, then the p-adic absolute value of 25 with respect to the prime number 5 just equals, well, 25 is 5 squared. So its absolute value is 1 over 5 squared. Okay? So you just divide by the power of p that fits into the number itself. And it turns out this is an absolute value. So it's a norm. And it's only one of infinitely many, but countably infinitely many. There's as many of these, as many norms you can put on integers as there are primes, plus the regular absolute value. And so that means you can complete the integers, or even more generally, the rational numbers with respect to this p-adic norm. And so what you get are these p-adic numbers. And so when you're considering the completion with respect to a norm, you're really talking about Cauchy sequences. Well, yeah, I don't have to erase, so maybe be consistent at least. Okay, so that means that you take z, you complete it, you get something that's called zp, and it consists of these Cauchy sequences. In other words, things like a0 plus a1p plus a2p squared plus a3p cubed, and so on, with each ai inside the set from 0 to p minus 1. So it's any integer between 0 and p minus 1. In other words, formally, this is just the limit as n goes to infinity of rising sums from I equals 0 to n of ai p to the I. Okay, and it also equals the inverse limit of z over p n to the z. So in other words, a p-adic number is an integer embedded in as a p-adic number. You write as a series in p, where you're giving modulo, you're giving it more and more precisely modulo higher and higher powers of p. Okay, you're just expanding numbers in terms of p, and then you complete this to just have something complete. And by the way, if you start with q, and then you complete q with respect to this p-adic norm, you get qp. And then you construct its algebraic closure, because it's not algebraically closed. Well, is this complete? It isn't complete. Then you have to complete it again. And you end up with something called CP. And this CP is both closed and complete. So this is where the process ends. You have some closed and complete thing. And the idea is, you know, if you start with Q and you consider just its completion with respect to the regular absolute value, you end up with complex numbers in algebraic closure. But here you end up with something different. You end up with this CP guy. And it allows you to do analysis. That's the point. And that's a small amount of which we'll do today. So let me try to define the equivalent of the character formula I talked about before. The Teichmuller character. So let me start with a lemma. This lemma is called Hensel's lemma. Hensel, I think, first started dealing with these p-adic numbers. He wrote something like -1 equals 4 plus 4 times 5 plus 4 squared times 5 squared, and so on, because this is the p-adic expansion in Z5 of -1. You can verify for yourself that this is actually true. In fact, maybe that's something we can do in the problem session. It's very easy. But, you know, he wrote this expression, and he said any sensible mathematician will look twice at this expression. But let me tell you a little bit about it, and then he kind of developed some p-adic analysis. And one of the things he developed was this Hensel's lemma. So what does the lemma say? So let p of x be a polynomial with coefficients in Zp. Okay? So this is any polynomial. And now, suppose that f of a0 is congruent to 0 mod p, but that f prime, the formal derivative of this polynomial, evaluated at a0.
It's p of x. Yeah.
Oh, gosh. Yes, thank you. Right. So f is the polynomial. So f prime of a0 is not congruent to 0 mod p. In other words, and a0 here is some p-adic integer. In other words, a0 is not a simple root of this polynomial reduced modulo p, okay? Because the coefficients of it are in Zp, they have an expansion of that form, and so it makes sense to reduce modulo p. So you get a polynomial with coefficients in fp, and you take a simple root, okay? Well, then what Hensel's lemma says, there exists a unique p-adic integer a such that the polynomial has a as a root and a reduces to a0 modulo p. Okay. So in other words, you can, if you have a simple root over fp, you can lift it to of a polynomial, you can lift it to a root in Zp. And the way you prove it is you start with a0, and then you use something that looks like Newton's method to find a1, the next digit, and then you use something like Newton's method to find a2. It's a very good exercise to do, but it would take, I think, the rest of the lecture. And you get an exact root. So somehow finding real roots, approximations of roots in over the real numbers. Here it gives you exact roots to polynomials, which is a great result. Okay, so roots of polynomials over FP, simple ones, lift to ZP. A0. Sorry, I should have said from the beginning in FP. I said ZP, but when you reduce it, anyway. Okay. And so, that leads us to the definition of the Teichmuller character. So for all x in FP star, there exists a unique p minus first root of unity in ZP star, denoted Teich x, such that Teich x, or actually, you know what? I'm just going to use T of x to denote Teich x, is congruent to x modulo p. Furthermore, the map Teich, or T, from ZP star, sorry, from FP star to ZP star, defined by sending x to this root Teich of x, or T of x, is a multiplicative character and this character generates the group of characters from ZP to from FP to ZP. So all such characters. Okay. And what I mean by that is that powers of this character are going to give you different characters from FP to ZP, and that's all of them. In fact, ZP star is a cyclic group of p minus 1, so the group of characters you can prove easily is also of order p minus 1. And by character, I mean a multiplicative homomorphism from FP star to ZP star. And so this kind of determines how you go from ZP to FP, from FP to ZP. Let me illustrate the proof and why I mentioned Hensel's lemma in the first place. So elements of FP star are exactly the roots of some polynomial f bar x equals x to the p minus 1 minus 1. Okay? And so you can choose a lift f of x to be x to the p minus 1 minus 1. But this time you see it as living in zpx. Okay? And so you, by Hensel's lemma, each x in FP star has some root, call it, has a corresponding solution, t of x in ZP star, such that, well, t of x to the p minus 1 minus 1 equals 0. In other words, it's a root of this polynomial, right? And furthermore, T of x is congruent to x mod p. So the first digit of this number, in p-adic digit of this p-adic number, is just x. And x is a number, you can take an integer representative of this number in ZP. Okay? And now, there's some work to be done to show that this is a multiplicative character. In other words, T of x is a homomorphism from ZP star to from FP star to ZP star. So to show, let's see, since a product of roots of unity is a root of unity, you have that T of x times y, T of y to the p minus 1 just equals 1 in ZP. Okay? But also, T of x, T of y equals T of xy. Sorry, is congruent to xy. So now that means that you have a root of this equation that reduces to xy, okay? And xy is just some number in FP star. So by the uniqueness part of Hensel's lemma, ty equals just t of xy. Okay? And this proves that t is a multiplicative character. And next, you need to prove that the powers of t, so if I send x to the t Teichmuller to some power, is also a character, but this I'll leave to you as an exercise. It's not very hard. It's actually, there's a very, yeah. It's not hard at all. Okay, so I promised that this was in some way an analog of the character formula I mentioned before, where you're adding x to the sum power over all elements in FP. So we're going to do something similar here. We're going to get a certain character formula. And so if T of x denotes the Teichmuller character, then we have the following formula. Sum over x in FP star of Teichmuller x to the ith power equals 0 if I is not congruent to, or sorry, let's do it the other way, because, oh no. It's 0 if I is not congruent to 0 mod p minus 1. And it's p minus 1 if I is congruent to 0 mod p minus 1. And so this is proven in exactly the same way as the other proof went. You just replace, every time you see an x, you replace it by t of x. And because it's a multiplicative character, you can do the same trick where you have t of y distributes into the sum. The multiplicative character t of y times to the ith power times t of x to the ith power combined together to t of xy to the ith power. So it's important that Teichmuller is a multiplicative character. And you get this summation formula. Okay. So that's the Teichmuller character. It's important for counting points. It's the analog of the previous formula, but it's not enough. The name of the section is character formulas. And so there's another character, but this time it won't be a multiplicative character, but rather an additive character. So it's going to go from FP to ZP, and it's going to satisfy the property that it sends x plus y to the character of x times the character of y. It's called the Works character. And since I'm running out of time, oops. I think I'm going to start cheating a little bit. Do people understand what's going on? Okay. So the works character is an additive character. And as I said, I call it theta from FP to CP star. In fact, it'll just go to ZP, but why not just say this? Constructed as follows. Let epsilon be a pth root of unity in CP. Okay. Did I say ZP is enough? I think an extension of ZP is enough. If epsilon is a root of unity, define theta of x to be epsilon to the Teichmuller character of x. So now I claim that this is an additive character. And why is it an additive character? Well, note that Teichmuller of x plus y is the Teichmuller of x plus the Teichmuller of y plus p times some z, where z is a number in ZP. Maybe it's not too hard to show, but you should trust me. And what does this imply? Well, this implies that theta of x plus y, okay, equals epsilon of Teichmuller of x plus Teichmuller of y plus p times z. But since epsilon is a pth root of unity, this term goes away. And this just equals epsilon Teich of x times epsilon Teich of y, inconsistent notation. And this is just theta of x times theta of y. So we now have automatically an additive character from FP to ZP. Okay? And this is the guy. And so we have two characters. One is additive, one is multiplicative. And now we want to look at them together. And maybe you've dealt with this in a different context, but there are these things called Gauss sums. We're doing exactly that. So define for n an integer the nth Gauss sum to be the sum over all elements in FP star of the product of these two characters, one multiplicative and the other additive, where we're taking the Teichmuller to the n multiplicative character. So there's p minus 1 of these guys, really. So this g to the n depends only on n, the class of n in FP. Oh, sorry, modulo p minus 1. Because the powers of the Teichmuller generate all the multiplicative characters, and there's only p minus 1 of them. There's Teichmuller, Teichmuller squared, Teichmuller cubed, up to Teichmuller to the p minus first. Okay. So this guy is a Gauss sum. And now it turns out these Gauss sums are meant to be an analog of the gamma function. And they're sort of the correct p-adic analog of the gamma function. There is a thing called a p-adic gamma function that isn't this Gauss sum, but it is closely related. So it's the same thing up to a constant. There was a big theorem that sort of showed that this guy is the p-adic gamma function up to a constant, where the p-adic gamma function is just like the gamma function, or just like the factorial with like with some terms removed and then made to be analytic with respect to this new topology of the p-adic number. So you have a different norm. It's beyond the scope of this talk. But the point is, an analog of gamma to the s equals the integral from 0 to infinity dt over t of t to the s e to the t. And I say it's an analog because the character x being sent to x to the s correspond to this multiplicative Teichmuller, okay, t of x. Both are multiplicative. Then furthermore, the assignment x goes to e to the minus x correspond to this dwarf character. Both are additive. And the integral with respect to this Haar measure simply corresponds to summing over x and fp star. And in fact, this relationship, this analogy goes beyond just face value, where you can do proofs for identities satisfied by the gamma function in the same way as proofs for identities satisfied by this Gauss sum, because somehow the proofs only depend on these on properties of characters. So really, the characters are key to understanding Gauss sums. And I'm getting to the point of why you care.
Is this e to the minus t?
Oh, yes.
Only extended it cannot be like
No, so it takes values in p-adic numbers in this case. So I'm defining it this way. So there's another concept, right, of Gauss. There's many kinds of Gauss sums. And you're probably thinking of as defined here? No. So so this Teichmuller works for, so if you take an integer, that integer corresponds to some number in fp. You just take the class that it corresponds to. And the same thing is true for theta, because theta was defined in terms of the Teichmuller. So this is actually well defined for any. Remember, Teichmuller is a character from fp to zp, and dwarf here is a character from fp to zp. So you're plugging in something in fp, and you get a product of things in zp, and you just whatever it is. And there's you're probably thinking of Gauss sums, the different Gauss sums which exist, but they're distinct. Okay. In any case, I mentioned that identity is satisfied in the classical sense are satisfied here. So analog of the inverse Mellin transform e to the minus t equals 1 over 2 pi I, integral of c minus I infinity to c plus I infinity, where c is something in the c is a real number greater than 0, and the real part of t is greater than 0. There's some condition, and you also need to think about the branch of something in here. It's just g of s t to the minus s ds. Okay, and now the analog of this well-known formula is just, as you would expect, theta x equals 1 over p minus 1, sum from m goes to 0 to p minus 2 of g to the minus m, the g of minus m, so the minus mth Gauss sum, t to the m x. It's actually, it takes maybe 15 minutes to prove. And so now we come to the punchline. So we developed all this stuff using all these character formulas. Why should you care? me write it here. Well, you can compute the number of points using this. So consider, since theta is an additive character, and yet again the same way as proving the original character formula, you can prove that the sum over x and fp of theta x equals to 0. Okay? Easy to prove. Because this is not a trivial character. It's proven the exactly same way as before. But just take it as face value. Then the expression, the sum over all x in fp cubed, so triples of x1, x2, x3, summed yet again over all y in fp, let's say fp star, or let's say fp, equals, of course, of theta y times p psi of x, or p psi is now, I'm taking it to be the Fermat cubic polynomial, but you can take it to be any other polynomial. This equals p times the number of points on the curve, on the hypersurface with coordinates in fp. And let's see why this is the case, okay? So for every triple x1, x2, x3, for which p of x vanishes, you're adding theta of 0 p times, okay? When you add, theta of 0 is an additive character, so theta of 0 goes to 1. So it takes the identity, the additive identity to the multiplicative identity. And so you get p times the number of points, as long as whenever you do not have a solution, this sum is 0. But it is 0 because if x1, x2, x3 plugged into here, so this sum, the inner sum disappears, is not a solution, then y times not a solution is going to be a non-zero number, theta of a non-zero number, added over all y in fp. And so those terms indeed do all disappear because of this character formula. And so now you have an expression for counting points, and you have this way of expanding the expression into simpler characters. So now I have, if I have my polynomial, I can expand, I have a sum of terms in the polynomial. So this additive character decomposes the sum of terms into a product of the same character. So if p equals, remember, x1 cubed plus x2 cubed plus x3 cubed minus 3 psi x1, x2, x3. Then theta of p just equals theta of x1 cubed times theta of x2 cubed times theta of x3 cubed times theta of minus 3 psi x1, x2, x3. Okay? And each of these terms I can expand using that formula. And now I get a bunch of sums over x1, x2, x3, and y of Teichmuller characters in x1, x2, x3, and y. And I have that character formula over there for when that sum is 0 or not 0, which amounts to solving equations like in the first case of something being congruent to p minus 1. And when you solve these equations, you end up with a calculation for the number of points, which corresponds to the period integral from the very beginning. And I'll focus on this in more detail next time I talk, when I'm computing the zeta functions for pairs of mirror manifolds, which is essentially you just use these techniques to do. And that's all I have to say. Yeah.
So it happens, obviously, you're getting the same formula for computing periods, you have these points. But I don't see exactly how mirror symmetry committed that.
Yeah, well, so it doesn't really. I mean, until later. It comes in where, so if you take the quintic threefold and it's in the mirror, right, you quotient by some group. and you compute the zeta function of some kind, two kinds of surfaces, then it turns out that the congruent zeta functions, they're rational functions in this case, and they share certain terms. The polynomial factors of them are the same. Some of them are the same. And it's in a very predictable way that they're the same. And so this is where mirror symmetry comes in. People start noticing these correspondences between zeta functions of mirror manifolds. And the real answer is more complicated, but.
Yeah, so when you look at the Perunicic case, it's because H11 is 1. So, but there is also, the Perunicic 202, that's too many, right? So you go to the mirror side and you compute the period on the mirror, that's the current differential equation of order 4. And then we wrote down this first solution, that's the first holomorphic solution. So these 4 solutions, they are common to original Calabiano and then negative. So that's what is happening with this calculation. More questions? Okay, so we'll work out. So I don't know everything in the afternoon. Any questions, problems? And meet tomorrow. Yeah. Or point is you learn something. Okay, this is a graduate course, so yeah.
Actually, on that note, I guess we should take a lunch break right now because, and then I think both of us have listed some problems we thought that are sort of doable, to sort of work on. So it is currently obviously just short of 12:30. Maybe if we meet back here at 1.
Yeah, so this room will be taken up to
Not back
2:30 or something.
Okay, I'll figure out, maybe if we can meet in the that area
So
there.
either
and maybe
library or
the library or the next one over, I'll figure out that, and then we can just start with the problem.
If you're looking for a place, the NAP building has like a bunch of tables sitting nowhere.
The library up there would be fine. Or the room across the way, assuming they're.
Oh, you mean in here? Like?
Yeah, if we can stay in this building. Anyways, I think we'll be back here at about 1:30 then.
If you brought lunch or something.
Oh yeah, that's the other thing, we're gonna eat lunch.